feel like we should have over.
No.
I should. Okay, so these subduction zones, and this is slide number 29 if you're with us at home. Subduction zones are pretty cool because, if I backtrack for just a second, when that ocean crust subducts beneath the continental, it gets put back into the magma, which melts it. And so basically it is recycling that old oceanic crust that was being pushed to the edge because the seafloor is spreading at a divergent boundary. And so if things keep pushing, at some point it's going to run into something else, causing a convergent boundary, and that's exactly what happens. Okay, and so here's what happens for words, like we've kind of discussed it, but the old oceanic crust that was originally made during that seafloor spreading converges, comes together or collides with a continental crust. And since it's more dense, it subducts beneath it, ducks down. And once it's underneath the continental crust, it gets shoved back into the asthenosphere, gets superheated, and melted back into magma. So that's why we never run out of magma at seafloor spreading. If you would think that the crust is separating, and this is happening, remember the mid-Atlantic ridge? All the way from the southern part of the Atlantic all the way to the North Atlantic. It's like a 10,000 mile mountain range where it's constantly being pulled apart and new magma's coming up. That's a lot of magma that's being used, and that's in just one of those mid-ocean ridges. So if that's happening, you would think at some point you'd run out of magma. But this process here ensures that constantly you are putting new, old oceanic crust getting put back into the magma to make new magma.
Eventually, would the continents or like the plates recline?
So that's a good question. If we have another couple billion years, let's see what happens, right? It might. The Earth has been in existence for 4.6 billion, and the continents have shifted. At some point, will it kind of continue and like meet on the backside of the Earth and form a new Pangea? Maybe, right? I mean, technically, you would think that that would eventually happen, right? But again, that's billions, not even millions, but billions of years into the future. So I guess time will tell, but there's no reason to think why it wouldn't. Okay, so here's our magma. You can see the new crust, then the old crust, then it subducts, becomes back in the asthenosphere, becomes magma, and then it has a chance of coming back up to the surface. Now, it doesn't always come back and become new crust at mid-ocean ridge, but it could. Okay? And so besides the oceanic crust getting recycled, yes?
Would it have the potential to create underwater volcanoes once doing that?
It could. Yeah, it could. Depending on, it all depends on like the crust that's above it. If it's thin and there's like a soft spot or something, it can come up. If there's a crack, it can come up through the crack. So it kind of depends on the crust that's above it. So besides that cool recycling factor, the other thing that happens there is volcano action. Sorry, I probably went too fast. All right, so if you take a look at this picture, here's our magma, here's our mid-ocean ridge, right? So here's our seafloor spreading in divergent oceanic plates. The new crust here, old crust here, it's being pushed into the continental plate. This is now a convergent boundary right here. And so as this happens, you can see that there's these little plumes, it looks like, little pockets of magma that's kind of coming up. If there is some cracks or weaknesses in the crust, because you have this accumulation of old crust getting melted, you get kind of a lot of pressure or a lot of extra magma in this area. So some of that can kind of ooze up if the crust is right, like if it's got some cracks or if it's soft or something like that. And so when that happens, you can get a line of volcanoes that will form along the coastline because that boundary is all along. It's not just like one point, it's the whole length of the plates. Tristan, don't be ornery. Sorry, it takes all the fun out of it. Because you have that abundance of magma and heat right at the where the plates converge, volcanoes are often gonna form there. And they will form parallel to the coast. Okay. So, subduction zones, volcanoes, those are some really important things that go with convergent boundaries. It is easy to confuse all the things that go with each type of boundary. Think about logically what's happening. Think about divergent, and you think about the seafloor spreading, and then think about the mid-ocean ridge that can form there. If you think about a convergent, when they come together, obviously when things come together, if they're the same density, it's just gonna kind of like, mangle and fold on itself like a mountain. Or if one is more dense, it will go beneath, forming a subduction zone and then forming volcanoes along that coastline. So if you think logically about what is going on and not try to memorize these events and features, you will have a much better chance of remembering how things, what goes with what. All right, so think about it logically. Here's a way to remember reverse faults. All right, so reverse faults go with convergent boundaries. Normal went with our divergent. The reverse, well, guess what? Instead of one dropping down like it did in a normal fault, what do you think is going to be the opposite or the reverse?
Shooting up.
One's going to pop up. All right, think of the demolition derby. When you have two cars, typically one's going to hit and go over the other car. So if you have two plates coming together, pushing, boom, one's going to pop up. We call that a reverse fault because it's the opposite of the normal fault, which drops down. So with the divergent, they were pulling apart like tug of war, and then one side cuts loose, one side falls down. That's what you would normally expect to happen when things are pulling apart and one side lets go. So if you have the opposite coming together, when they come together, the reverse of falling down would be popping up, and that's what happens. So you have them pushing, 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 and one side goes up. Think about those examples. I can't remember normal versus reverse. I have to think of those little examples to help me remember. I don't know, or find something that kind of makes sense to you to help it make sense. But it's at a fault line, which is in that response to that stress, that pushing, you're going to see that cracking, and the way it's going to behave is going to pop up. Okay? And it's called reverse because it's the exact opposite of what goes on at the normal force. Or excuse me, the normal fault. All right. Our third and final boundary is a transform boundary. Okay? And so it's kind of cool. You can see here, look at these rows in this field. Look how they're offset. They're traveling and they kind of sidestep each other. Okay? You can see here with the river, right, it's offset. So I know that this is a fault line right there. Now, in the movie San Andreas, they show a fault line, and they definitely give it the Hollywood aspect to it, and they make it real dramatic. Typically, you're not going to see something extremely dramatic like they showed, but it's still pretty good. So these are going to be forces in the Earth's crust that cause plates to travel side by side, which is like sliding past each other, right? Transform boundaries travel side by side. So when the plates move suddenly, they cause vibrations, and we feel those as earthquakes. Yes?
Negative.
Yes, good. So there were earthquakes with divergent, there were earthquakes with convergent, and there's earthquakes with transform. So you have earthquakes possible with all three types of boundaries. That's the only thing that all three of them, or event or feature that they all have in common. Earthquakes at all three. Okay? And so here you can see the plates slide in opposite directions. They can also be traveling in the same direction, but one of them is traveling faster. And that's a little bit weird to think, like opposite directions, okay, yeah, you can only stick for so long before it's gonna slide. Think about, and when I used to teach 5th grade, I would watch you guys, or maybe not you specifically, but watch kids running around playing tag, and they're like, oh my gosh, come here, and they grab in their friend's hand, they're like, come on, come on, come on, come on, right? You're pulling your friend along, right? Maybe more of the girls than the boys, but you can imagine, right? One friend is pulling the other friend's hand. Well, if the first friend is faster, she's gonna be pulling, 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 and she can only hold on to the slower friend's hand for so long before they can't hold on anymore. And so they're going in the same direction, but the one friend is moving faster. So they're holding, 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 holding until they can't hold anymore, and they slip. And what happens at a transform boundary is they get a strike, slip, fault there. When it actually slips by, that's when you feel those vibrations or that earthquake occurs. So opposite directions or traveling at different speeds. Either way, you're gonna get that strike, right? That slip, or that strike, and then the slip, right? So that fault does kind of like what the words sound like. So the fast friend running, 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 can't hold on to the slow friends, and they slip. Here's what happens. Remember how on Friday you had that weird font and in bold? Those were the key things I said are really important that you need to know for each boundary. Well, here's the strike, slip, fault, and earthquakes. Those are the only two things that happen at a transform boundary. So kind of end on the easiest one. Okay, very important. You can see this building, it's kind of hard because it's small, is split in half. So one half, like it just so happened to be straddling a fault line. And so when it experienced that slip, it split that building down the middle. And so the strike, slip faults at a fault line is where the two plates stick or strike and then slip by one another. Again, doing exactly what the word sounds like. And this movement causes vibrations and are what are responsible for earthquakes. And again, earthquakes are the only event that happens, right? So no volcanoes, no seafloor spreading, it doesn't matter. Now, this can happen at continental to continental, can happen with oceanic to oceanic, it can happen with either of them, with either types of crust. If you get an earthquake that forms, or if you get a strike slip fault that happens in the ocean, what else can happen? What else could it trigger? Anybody know? A tsunami. And we'll talk about that a little bit more, maybe today if we get to it, or maybe tomorrow, for sure. So the most famous one is the San Andreas Fault in California, at least in the United States for sure. So San Andreas Fault line. All right, so again, the motions, right? Convergent, divergent, transform, okay? And so we'll skip the song. Oh yeah, we're doing good, and we will come back to that. All right, so I want to cover a few things that go along with these different types of boundaries. So a tsunami is going to be the high sea wall that of like a big giant wave that is going to basically start with the vibrations caused by an earthquake. And so out in the middle of the sea, it's going to cause a wave, and that wave is just going to keep traveling and traveling and traveling until hopefully it like runs out of energy. But if it reaches land while it still has that giant wave, it's going to reach landfall and cause sometimes some devastating, catastrophic events. We have a video that we're going to watch, but it's like 45 minutes. So we're going to watch that after the air test. And so we'll come back to that. I already have it marked that we will get to watch that afterwards, so that, but you can kind of see, here's a coast town, and you see that giant wave or wall of water coming. Most towns, that are in this situation, like where they know that they could be a recipient of a tsunami, have tsunami warning signs. So when an earthquake is detected out in the ocean, it sends an alert once it reaches a seismograph station, and it sends alerts to those towns saying, hey, an earthquake just happened, you know, possible tsunami, and like it gives them enough time to prepare. And we'll see that on the video. Geysers, right? These are hot springs where you have water that boils and it sends a tall column of water into the air. So the water beneath the surface gets, like, so the groundwater gets superheated because the heat from magma. And so then it builds up all this pressure, and it's just kind of like a tea kettle. You have it on your stove, the water starts boiling, it builds up pressure, and then it's like kind of spurts through. That steam starts spurting through that top part of the tea kettle. So if you've ever been to Yellowstone National Park and seen Old Faithful, that is a form probably of our most famous geyser that we talk about. Hot springs. This is a spring of naturally hot water, typically heated by subterranean volcanic activity. When I was in Ecuador, I had the awesome experience. We were up, it's kind of weird, we were actually kind of like in this mountain village, and it was known for, and I mean, we're talking village, like it was very, very primitive, like no roads, like they had a little couple buildings and shacks and things, but there was this huge lake that was a hot spring. So it was really cold, like we were bundled up, because we were in the mountains and it was cold. But there was just this random lake, and so we're like, oh, this is kind of crazy. Like, so we went into this little like lodge thing, and we all got changed into our bathing suits and stuff, and like we had our coats on, and like we run to the lake, and you get in, you could only be in there for like 10 minutes. It was so, like, it wasn't just warm, it was hot. It was like as hot as a hot tub. And I mean, it was just steaming because the air was real cold. And like you'd get out and your skin would be all red and hot, and like it'd feel good to be in that cold air. But it was really kind of cool. So it's basically like a natural hot tub. Very, very interesting. And I had no idea that it would really be that hot. Like I thought, okay, it'll be like warm water. No, it was hot. Hot spots. So this is a small area or region with a really hot temperature compared to its surroundings. So maybe the crust is a little bit thinner there, and so the magma that's beneath it has a way to kind of get to the surface, and a lot of times this is happening with oceanic crust. So the surface is then covered by an ocean of water, right? A whole big ocean above it. And this is actually how the Hawaiian Islands formed. And so you can see these red dots are known hot spots. And a lot of times, I don't know if it was Tristan or Cameron, one of you asked I think it was Cameron, asked if that's how underwater volcanoes can form. Yes, so you have that crust that's a little bit thinner, and so that magma can start oozing up, and as it oozes up, it starts to cool, and then more magma pushes up, and so you get these shield volcanoes that form, and that's how the Hawaiian Islands are formed.
Can I use the restroom?
Yes, go ahead. All right. And then rift valleys. So we had talked about this. This is like the Laffy Taffy that you pull apart. So continental crust pulling apart, getting thinner and thinner and thinner in the middle. And you can kind of see that from that picture. It usually doesn't get thin enough where magma will come up like that it does at oceanic crust, because remember the oceanic crust is so thin. But that thick continental crust can get spread and spread and spread so that it's thin in the middle. And then you get these, kind of the warping, and looks like a valley, but it's kind of rough looking. So we'll watch this video that's going to show this here in a minute. I don't know if there's another one. Let's do this one too. So there's these things called ocean vents. Think about like a heating vent or duct like in your house. It's where like hot air in the winter or cold air, if you have centralized air conditioning, will come out of that vent in the summer. So this also happens way down at the bottom of the ocean. So you get these little cracks or fissures in the crust, right? And then seawater, which is freezing cold, because it's at the very, very bottom of the ocean, is gonna drip down into those cracks, right? And when that happens, that water gets to where it's hot, where the magma is, and it causes that, it kind of like pushes steam back out that tiny hole. So you get these areas where hot steam is pushing out into the very, very, very cold ocean water. So you get some really cool, unique ecosystems associated right there at those vents, because typically the ocean water is freezing cold, and then you have this random spot where hot water is pushing out. And so it's kind of cool. And this is basically like what happens even like at the surface with a geyser. It's kind of the same kind of process. It all has to do with water that shouldn't be getting superheated, gets superheated, starts to boil, steam builds up, and then pushes to release. But this is happening at oceanic crust, and so then it warms up that water right in that area where that vent is. So the cold seawater gets heated by the hot magma and then re-emerges from that vent. So the water trickles down the crack, gets superheated, and then gets forced back out the crack. And it is superheated, like 700 degrees Fahrenheit, which is crazy because you're near water that is close to freezing, right? And then you have that hot of water shooting up, meeting that cold water. And then there's these things called island arcs. And an island arc is a type of archipelago, which is a group of islands, that are composed of a chain of volcanoes in kind of an arc shape that run parallel to a coastline, usually between two convergent tectonic plates. Right? And so if you look at this picture, convergent means they're coming together. So guess what forms here? What kind of zone, not an autozone, what kind of zone is going to form here? A subduction zone. So then you have this accumulation of magma, and look at this line of volcanoes that forms. So we call those island arcs. Okay. Did I say we're done? You're done? Pack it up. Or are you just switching pages?
Yeah,
Just switching pages? Okay. Let's take a look at let's watch this Rift Valley one. I think that the time is good for that one. And then we still have time